In this lecture, we'll first learn how a star's mass affects nuclear fusion, and we'll also cover the life stages of a low-mass star, including what happens at the end of its life. In the last chapter, we studied the battle between gravity and thermal pressure as the molecular cloud transforms into a star. For most of a star's life, pressure and gravity are balanced and the star is stable. But eventually, a star will run out of hydrogen fuel. The battle begins again, and this time it's even more dramatic. What happens in the end depends entirely on the star's mass at birth. Main sequence stars with large masses have much greater luminosities than low-mass stars, and they fuse hydrogen into helium at a much faster rate. A star's mass also determines what happens when the star finally exhausts its core supply of hydrogen. It's the mass that determines whether it eventually becomes hot enough to fuse helium or heavier elements. Even at the end of its life, when a star runs out of its last bit of fuel and can no longer fuse anything, the star's fate will depend on the mass it had at birth. We can divide stars into three basic groups by mass. Low-mass stars are stars born with less than about 2 solar masses of material. Intermediate mass stars have birth masses between about 2 and 8 solar masses of material. And high-mass stars are stars born with masses greater than about 8 solar masses. The life stages of intermediate mass stars and high-mass stars are quite similar up until the very end of their lives. We'll begin our journey through stellar evolution with the life of a low-mass star. This mass category includes our Sun, so you're about to learn the ultimate fate of our parent star. Remember, low-mass stars are stars that were born with less than 2 solar masses worth of material. In this low-mass category, we're looking at stars of spectral types M to A. Our Sun is right in the middle at G2. This corresponds to a surface temperature of about 5800 Kelvin. Our Sun is on the main sequence, fusing hydrogen, but eventually, in about 5 billion years, the Sun will exhaust its hydrogen and undergo a series of dramatic changes leading up to its death. We'll approach our study of a low-mass star's life by looking at what will happen to our Sun. As we learned earlier, the Sun slowly and steadily fuses hydrogen into helium via the proton-proton chain. Gravitational equilibrium and energy balance work together to keep the Sun's fusion rate and overall luminosity quite steady. This is the case for all low-mass main sequence stars. A star like our Sun will happily fuse hydrogen into helium for about 10 billion years. But once its hydrogen is finally depleted, nuclear fusion will cease. With no fusion to supply thermal energy and maintain the interior pressure, our star will be out of energy balance for the first time since it was a protostar. It won't be able to resist the crush of gravity and the core will shrink. Strangely enough, even though the core is shrinking, the outer layers will expand and cool. We can follow the Sun's life track on an HR diagram as it goes from a main sequence star to a giant star. After it turns off the main sequence, the Sun will move almost horizontally to the right as it grows in size to become a subgiant. Then, as the expansion of the outer layers continues, the Sun's luminosity will begin to increase, and its life track will turn upward on the HR diagram. Over a period of about 1 billion years, the Sun will slowly grow in size and luminosity to become a red giant. At the end of its red giant stage, the Sun will be more than 100 times as large in radius and more than 1,000 times as bright in luminosity as it is today. So let's talk about why the outer layers of the Sun expand as the core shrinks. After the core exhausts its hydrogen, it will be made almost entirely of helium because helium is what we get from hydrogen fusion. The helium has been building up in the core all this time, but around the core there is still some fresh hydrogen that has not been fused. Since the hydrogen is running out in the core, the fusion reactions slow down. When fusion slows down, the core and the hydrogen shell surrounding it both shrink. The shrinking makes the shell heat up, and soon it's hot enough to fuse its hydrogen. The shell fusion proceeds at a much higher rate than the hydrogen core fusion did. This increase in energy output will cause a buildup of thermal pressure inside the sun, which will push its surface outward. The sun will become a huge red giant as seen from the outside, even while most of its mass remains buried deep inside its shrinking core. As the hydrogen fusing shell fuses, it creates helium and then dumps that helium onto the core. The helium core gets more massive and gravity causes it to shrink. The core becomes hotter and denser. So far, the helium core hasn't been doing anything. It's inert. Therefore, it can't expand to balance out this extra pressure. Core and shell continue to shrink and heat up, but the star is becoming larger and more luminous. Once the core reaches about 100 million Kelvin, it will be hot enough for the helium nuclei in the core to fuse, and the sun will enter the next stage of its life. We expect other low-mass stars to expand into red giants in much the same way as the sun will. As you might expect, the process occurs faster for more massive stars and more slowly for less massive stars. Fusing helium nuclei takes more energy than fusing hydrogen. Each helium has 2 protons, which will repel one another more strongly than hydrogen nuclei. Helium fusion therefore occurs only when nuclei slam into one another at much higher speeds. Helium fusion requires much higher temperatures than hydrogen fusion. The helium fusion process converts 3 helium nuclei into 1 carbon nucleus. Energy is released because the carbon-12 nucleus has a slightly lower mass than the 3 helium-4 nuclei. There's one weird thing about helium fusion in low-mass stars like the sun. The main pressure in that inert helium core is degeneracy pressure, the same unusual type of pressure that supports brown dwarfs. Degeneracy pressure does not increase with temperature. Therefore, when helium fusion begins, the core temperature will rise rapidly and the core can't expand to compensate. The temperature and helium fusion rate spike drastically in what is called a helium flash. After the helium flash, the temperature rises enough that thermal pressure soon surpasses degeneracy pressure and the core can expand. The core expansion pushes the hydrogen fusing shell outward, lowering its temperature and fusion rate. The outer layers contract a bit and the star's surface temperature increases, so its color turns back toward yellow from red. At this point, the star regains the same sort of balance it had as a main sequence star, except now it is helium fusion that keeps the central temperature steady. We can again follow the life track of the star on the HR diagram. Because the helium core fusion star is now smaller and hotter than it was as a red giant, its life track on the HR diagram drops downward and to the left. The helium cores of all low-mass stars fuse helium into carbon at about the same rate. Therefore, these stars all have about the same luminosity. The outer layers of these stars can have different masses depending on how much mass they expelled through their stellar winds. Stars that expelled more mass end up with smaller radii and higher surface temperatures, and hence are farther to the left on the HR diagram. Stars that lost less mass are cooler and to the right. We can see examples of low-mass stars in all the life stages we have discussed so far by looking at an HR diagram of a globular cluster. we can clearly see the main sequence turn-off point, subgiants, red giants, and stars just about to have a helium flash. The stars that are burning helium in their cores, that all have about the same luminosity but different surface temperature, these trace out a horizontal line on the HR diagram called the horizontal branch. Helium burning in the core will continue until the helium runs out. Our sun will fuse helium into carbon for about 100 million years. This is 1% of the time the sun will have spent on the main sequence. When the core helium is exhausted, fusion will again cease and the star will once again go out of balance. The result of helium fusion is to create a carbon core. Helium that has not yet fused is in a shell surrounding the inert carbon core, and surrounding the helium shell is the hydrogen-burning shell. As the helium runs out in the core, the fusion there slows down. The core and the helium shell both shrink and heat up. The shell gets hot enough to fuse the unused helium. We have a double shell fusion situation, a hydrogen-burning shell outside of the helium-burning shell, and no action in the carbon core. At this point, the star is not very stable. The helium fusion rate periodically spikes upward every few thousand years in a series of thermal pulses. With each spike, convection dredges carbon up from the core and transports it to the surface. The hydrogen and helium-burning shells won't last more than another few million years. The core will never get hot enough to fuse carbon, so we're getting very close to the end of the star's life. The double shell burning phase will end with a pulse that ejects the hydrogen and helium into space as a planetary nebula. Planetary nebulae have nothing to do with planets. The name comes from the fact that some planetary nebulae look like planets through small telescopes. A planetary nebula will fade as the exposed core cools and the ejected gas disperses into space. The nebula will disappear within 1,000,000 years, leaving the carbon core behind as a white dwarf. We will get into the details of white dwarfs in the next chapter. They are fascinating objects. For now, just know that white dwarfs are the exposed cores of dead stars. They are often quite hot, but eventually they will cool and no longer emit visible light. White dwarfs are supported by degeneracy pressure, which is why they can be so small and dense. A typical white dwarf is the size of Earth with the mass of the Sun. In summary, here are the life stages of a low-mass star. All stars begin as protostars. When the interior gets hot enough, hydrogen fusing can begin in the core and the star is born. It will spend the majority of its life as a main sequence star until the hydrogen runs out. It then leaves the main sequence, becoming a red giant star with an inert helium core and a hydrogen fusing shell. The core shrinks and eventually it's hot enough to fuse helium into carbon. It's now a helium fusing star. Eventually the core will be mostly carbon, surrounded by a helium shell. When that shell begins to fuse, we have a double shell burning red giant. Eventually, all the fusion ends and the star ejects its outer layers as a planetary nebula, leaving behind a white dwarf, the leftover core of the star. The sun's demise will affect Earth even before it enters the final stages of its life. The sun will continue to gradually brighten, and as it does, Earth will get hotter. Some climate models predict that the oceans will begin to evaporate about 1 billion years from now, while other models suggest that we may have more time. All models agree that by about 3 to 4 billion years from now, the sun will have brightened enough to doom Earth to a runaway greenhouse effect. This plot shows results from a theoretical model of how the sun's luminosity should change throughout its life. At the helium flash, the sun's luminosity will rise to 1,000 times its current level, heating the Earth to over 1,000 Kelvin. This is the theoretical model for how the sun's radius should change. Near the end, it will grow to nearly the current radius of Earth's orbit. The planetary nebula will engulf Jupiter and Saturn and eventually extend into interstellar space. I'll leave you with this lovely Hubble telescope image of the Helix Nebula. It's a planetary nebula located about 700 light years away in the constellation of Aquarius. I love this image. It's amazing to me that we're able to see this sort of detail. I hope you like it too. That's all for now. Take care. I'll talk to you soon.